let's look at formation of tri-substituted benzene and how these directing effects can add to one another. So if we're preparing a tri-substituted benzene, the directing effects of both of those groups in the starting material need to be considered. So there are often times, and this is our sort of best case scenario, where the effects will reinforce each other. So if I have para-nitrotoluene, the methyl group is an ortho para director, but we can't add para because the nitro group is there, so primarily ortho there. Meta to that nitro group corresponds with ortho to the methyl group because the two groups were across from each other. Okay? So the CH3 will tend to direct things right next to it. The nitro group across from the CH3 will push things meta to it, but that's the same position. So our sole product will occur at the ortho position, or that's ortho to CH3, and it is also meta to the nitro. So everything sort of converges, everything works out. Say I have two activating groups and they're in competition. Okay? I've got a paramethylphenol. I've got an OH on one side, a CH3 on the other side. Both of those groups will tend to direct ortho to themselves, but the OH group will direct next to it, the methyl group will direct next to it. The hydroxyl group is a stronger activator, okay, because it actually has lone pairs that can donate in. The methyl group only has its inductive donation, which is not nearly as strong. So those lone pairs will always win out. So the directing effects of the methyl group are not as important as the directing effects of the hydroxyl group. So we will add ortho to the hydroxyl group. The methyl group essentially just serves to block that para position from adding. So we do get one single product where I have an OH on 1, nitro on 2, and methyl on 4. If I have an activator and a deactivator in competition, the activating group will win. Here's my example. Let's do a benzene ring with a phenol. So let's do an OH attached, and then let's do a benzaldehyde meta to it. So meta-hydroxybenzaldehyde. The hydroxyl group, here I should color code these. Let's keep the let's make the hydroxyl red for the activating groups. OH is red. Blue for the deactivating group. C double bond OH. Okay. The hydroxyl group activates ortho and para to it. But since my original groups were meta, I will not add to the position between them because that's too much steric strain. Instead, the hydroxyl group will favor ortho and para to it. The benzaldehyde group will favor meta to it, which is different from ortho and para. But, like we said, if we have an activator and a deactivator, the activator will win out. That's because ortho-para directors are an actual stabilizing effect. Okay? They actually increase reaction at the ortho and para positions. The meta directors have a destabilizing effect at the ortho and para positions. So meta is just normal, not as bad as ortho and para. Okay? The hydroxyl group actually makes its ortho and para positions actually better. So we will end up with a mixture of two products, but they'll be determined essentially solely from that hydroxyl group. C double bond OH. Okay. So if we're, again, let's say we're doing Br2, we'll add ortho to the hydroxyl, or we'll add para. To the hydroxyl group. One more consideration, just like we mentioned before, steric hindrance or steric strain prevents addition of an electrophile directly between two substituents. So if I have metachlorotoluene, we'll be directing ortho and para to both of those, which is just next to both of those, not to the position in between them. So we'll get a mixture of products where the electrophile adds next to the chlorine or the electrophile adds next to the methyl. We may try to do something like this to get this 1, 2, 3 tri-substituted product, but we can't do that by putting one in between two others. What we have to do is start with two next to each other and add a third one next to those. So ortho-nitrotoluene, we favor ortho and para to the methyl group. We favor meta to the nitro group, but that's the same positions. So we will have a mixture of products, one that has that 1, 2, 3 substitution pattern that we were looking for, although nomenclature this comes from toluene, right? 2-chloro, 1, 2, 3, 4, 5, 6, 2-chloro, 6-nitro. I have to number going all the way around that way. But we'll also get the product where the CH3 and the chlorine are para to each other, but those can probably be separated out. Let's see if we can predict at which position electrophilic aromatic substitution would occur with these. I've got a methoxyl group, OCH3, so identify the lone pairs. Got a bromine. Okay. Both of those are ortho para, so identify the positions ortho. Okay. Here's ortho to OCH3, but that's in between two groups, so steric strain prevents that. Para to OCH3, ortho to bromine, para to bromine. So electrophilic aromatic substitution would occur at a mixture of those two sites next to both of those groups that are meta to each other, but not in between. All right, NH2 ortho to bromine. Both are ortho para, so let's do ortho to NH2. There and there. Okay. Ortho to bromine. There and there. We have two competing interests here. The NH2 is the stronger activating group. Remember, bromine is deactivating. NH2 is a strong activating group, so its positions will win. Bromine's will not. So we'll have EAS at those positions. Okay. The nitro group is a meta director, so meta to both of those. Chlorine is an ortho para, so ortho is there, para is there. The two forces are in concert, so we'll have a mixture of products at those two spots, just like that.